Hello everyone, I am Aditya Sauri. Today our topic is threaded binary tree. So we already know what is binary tree. Now let us discuss what is threaded binary tree. The linked representation of any binary tree has more null links than actual pointers. If there are 2n total links, here n is nodes, there are n plus 1 null links. A clever way to make use of these null links has been devised by Perlis and C. Thornton. The idea is to replace the null links by pointers called threads to other nodes in the tree. If the r child, here r means right child, is normally equal to 0, we will replace it by a pointer to the node, which would be printed after p when traversing the tree in order. A null left child link at node p is replaced by a pointer to the node which immediately precedes node p in order. Now let us discuss what is threaded binary tree and how it will be created with the help of examples. So here we can see a binary tree. So here it is the binary tree. So I took some nodes A, B, C, D, E, F, G, H, J, K. Now I represented this binary tree in linked representation. So we already know how to represent in linked list in binary trees. So here we have three fields. One is used to point out the left side node and another one is used to point out the right side nodes, and center is used to store the data. So in this way we can point out all the nodes. So left node, right node. So left side is used to store the left subtree's addresses and the right side is used to store the right subtree, that means right side nodes addresses, and remaining fields are empty because there are no another child nodes. For example, here E is there. For E we don't have any child node, so there is no chance to point out to another child tree. Like that only we have F, G. For G we have right side only, not left side. For K we don't have children's. For J, H. Now what we have to do with these left and right fields? If any child is there, we can fill it with that particular child addresses, but we don't have any addresses here, so we have to fill it with null values. So I am writing it as n. So n means null here. So here I fill it with null. In threaded binary tree, we use these null pointers. Here the concept is that we should not waste the memory. That means we are not using any address space at null fields. So here we are wasting so much of memory blocks because we are not storing any addresses of another child nodes. So here memory spaces are wasting. So in threaded binary tree we will give addresses for some of the null fields. So this thing is called threaded binary tree. So if we give addresses for some of the null fields, then it will be called as threaded binary tree. Now let us see how we have to give addresses to null fields. So we have so many null fields here in E node, F node, G, K, J, H. Now let us see how to give addresses. Now let us see some steps to convert a normal binary tree in threaded binary tree. So before discussing these steps, let us point out the left address and right addresses. So we already discussed this thing. And remaining will be null values. So we already know that. Now we have to fill the addresses in a null blocks. So we have some steps to convert normal binary tree in threaded binary tree. First, we have to keep the leftmost and the rightmost pointers as null. So here we have leftmost and rightmost. That means left side means these things. So here H will be the leftmost. So here it is the last element of left side. So we have to keep this element node as null in left side only. And we have another thing is rightmost. So here K will be the rightmost. So right side we have to keep this as a null. So we followed first step, that leftmost and rightmost null pointers as null. Now we have another step, that is change all other null pointers as, so left side pointers in order precedence and right side pointers in order successors. So we have to change these things as in order precedence and in order successors. So for left pointer only we have to assign in order precedences, and for right pointers, that means right side nodes, we have to assign as in order successors. So we already know what is in order. We already discussed these things in previous videos. If you have any doubt in this topic, you can go and check once. Now what is in order? So we have to visit the left node first, after that root node, after that right node. So directly I am writing the step here. Okay. So in order, H, D, J, B, E. So this is the in order. So first here we visited the left nodes, after that root node, after that right node. So for example, if we take D, so left side we have to take precedence, right side will be successors. Okay, so here we have H. For H we don't have any precedence, so it must be a null. So that's why here we gave so that's why here we gave null. Okay, after that, we don't have precedence, that's why here I applied null value for H, and we have successors. So successor is D. Changing the color for, okay. So we have to point out here. After that we have J. For J we have precedence and successors. So for J, precedence is D and successor is B. Okay, here we can check. and after that we have E. For E, the precedence is B, the successor is A. After that we have F. For F, precedence is A and successor is C. After that we have G. For G, precedence is C and we don't have successor because we already point out to the K only, and for K, G will be the precedence. So in this way we can fill some addresses into the null values. So here for H we have null value, so I stored D address here. For J, I stored D address and B address. For E, I stored B address and A address. For F, I stored left side A address, right side C address. So in this way I filled all the addresses in null values except leftmost and rightmost pointers. So remaining we fill it with some addresses. So this thing is called threaded binary tree. But we have a little bit confusion in this topic here, because here in H I stored some addresses, but what is the address? Is it child node or parent node? By using this diagram we can say it is the parent node of H, but while storing this thing in memory we don't know what is which element address is stored. So same problem will be arises for all the nodes. So which element, maybe it may be a parent node or child node. So to know this thing we have another technique. For differentiate that is parent or child, we have technique called threaded binary search tree. Threaded binary search tree. So by using this technique we can differentiate that it is parent or child. Now let us see how we can represent this thing. Here only I am writing. So left nodes. So here it is used to store the address of the left node, and here we use it to store the address of right pointer, and here we use it to store the data. And what is these things? So left flag and right flag. If the left pointer points the child node, the left flag will be 1. If the left pointer points to the child node, then we have to represent it as 1. If the left pointer points to ancestor, that means parent node, here we call it as ancestor. So here J is there and D will become the ancestor of J. Then left flag will become 0. I think you understand. If the left pointer points the child node, then left flag will be 1. If the left pointer points to ancestor, then the left flag will become 0. So in this way only, if the right pointer points to the child node, then right flag will be 1. If the right pointer points to ancestor, then right flag will become 0. So I hope you understand. So if we point out to the child, it will become 1. If we point out to the ancestor, that means parent, it will become 0. And here data will be stored, and here left node address will be stored, and here right node address will be stored. Now let us see how we can represent this thing as threaded binary search tree. Here we can see the threaded binary search tree. Now let us store the elements. Okay, so first we have A, B, C, H. So in data blocks we store the data. Now we have to point out the addresses. So we have to store the address of B in left side here, C here. So in this way we can store the addresses of the child. Now we have to find the left flag and the right flag. Okay, so by using threading binary tree concept only we can find this thing. So before going this topic, I would represent here in order. So we already know how we have to give this one. Okay, we already know here we have to store null. So because leftmost and rightmost should be null here. Okay, so now here D will become the ancestor, so we have to represent 0 here. Okay, after that here also it will become ancestor, so 0. After that for J so by using this previous example only I am implementing this thing. For A, so here also it will become 0. So that means successors. Here precedence. So left side will become precedence and right side will become successors. So here also 0. So F precedence is A. That means here also 0. And here we have to point out to the C. Here also it will become 0, and for G also it is successor, so 0. For K we have G. That means 0. Okay, and for A, so now we got the elements of ancestors. So when we are connected to ancestors, that means parent, we have to represent as 0 for flag. It may be right or left, we have to represent with 0 when we are connected with parents, that means ancestors. Now already we are connected to child, so that means for flag will be 1. So here for A we have two children, one is left and another one is right, so we have to represent it with 1. For B also we have 2, for C also we have 2, that means 1. For G we have only one child, that means 0 and 0. And right k, it is the rightmost element, so we have to represent it as null. Okay, for d also we have 2. Okay, so in this representation I give flags 1 and 0 if it connected with child. If a node is connected with a child, then I gave 1 as a flag, it may be right or left, and I gave 0 for ancestors if it is connected. Okay, so in this way we can represent the thread binary search tree. But here we have another problem. For h it is the leftmost, and for k it is the rightmost node, so that's why we make it as null values, but we have to fill the addresses in these two blocks also. Okay, so here h is the leftmost and k is the rightmost, because that's why we fill it with null values. So we already know why we fill it with null values only, but because for k we don't have another element after k, that's why I fill it with a null value. For h, so here we can see the h, so before h we don't have any value, so that's why here also I fill it with null, but we have to fill the addresses here also. So for that thing only we have to create a dummy linked list. Okay, so here we have to create this thing upside, that means topmost node, that means it will become the top for root node also. Okay, so here I created dummy. Okay, now we have to point out this here. So here it is the ancestor, so we have to give 1 here, and for this we have to connect to the right side. Here also it is the ancestor, so that's why I have to write 1 here, 0. So when we connected with ancestors we have to represent it as 0. If we connect with child we have to represent as 1. So we connected with ancestors, so we have to represent as 0. Okay, but we have another 3 blocks. One block, okay, for here, for flag position. For flag position only we have to connect, but we have 3 blocks, so we have to connect the left node. So we have to store the address of the left, that means here we have only one element, that is a, we don't have another. So when we are connected with a, it is the child, so we have to represent it as a 1. Then what about this thing? So we have to connect itself. Okay, we don't have another element to connect, that means we don't have another child element or ancestor element to connect, so that's why it have to be connect by itself. Okay, so if it is connected itself also, then the value will become 1 for flag. Okay, so in this way we can represent. I think you understand this topic. Okay, so this thing is called as threaded binary tree. I hope you understand. Thank you.